The film opens in silence, the cosmic kind, a whisper of light crossing endless dark. The narrator's voice cuts through. In every direction we look, the universe flees from us, not with hesitation, but with acceleration. Galaxies drift like lanterns on a rising tide of space itself. Yet for all our equations and telescopes, no one truly knows why. Time slows. The stars dissolve into streams of red-shifted light. What force pulls the fabric of existence apart? What hidden hand drives creation to scatter its own stars? The tone is somber, cosmic, introspective. The audience feels both awe and unease. The narrator asks, could this be the end of understanding, or the beginning of something beyond our reach? An intelligence embedded in space-time itself. A pause. Tonight, we journey to the edge of everything, to the greatest mystery in all of science. The universe is expanding, but no one knows why. High above the lights of Los Angeles, where the nights still belong to the stars, a solitary dome stood against the chill of the 1920s California sky. Inside, the 100-inch Hooker telescope, the largest of its kind, waited like an iron eye turned toward eternity. It was here, on Mount Wilson, that the universe would quietly surrender one of its deepest secrets. Edwin Hubble, a man of both science and silence, leaned into the eyepiece. He was not searching for wonder, only for truth. Yet in that pursuit, he would stumble upon something far greater than either. The faint smudges of light he observed were known as nebulae, pale spirals adrift in the black. To most astronomers of his time, they were thought to be clouds within our own Milky Way, gas and dust adrift between stars. The cosmos, it was believed, ended there, enclosed within the familiar sphere of our galaxy. But there were others who suspected something more. Among them was Henrietta Swan Leavitt, a quiet mind working in the shadows of the Harvard College Observatory. She studied the light of variable stars, Cepheids, that pulsed with precise regularity. She noticed that brighter Cepheids took longer to complete their cycles. It was not merely a coincidence. It was a law of the cosmos, a code written in starlight. Leavitt's discovery would become the yardstick by which astronomers could measure the true scale of the universe. Years later, Hubble took that yardstick and held it up to the sky. Using Leavitt's law, he calculated the distances to several of those distant nebulae. The numbers refused to fit the old model. These objects were far beyond the reach of the Milky Way, not within it, but beyond it entirely. Each spiral was a separate galaxy, a vast city of stars. The Milky Way, once thought to be the entire universe, was revealed to be one among billions. This realization alone would have been enough to alter the human story. Yet what Hubble found next would shake the very foundation of physics. While studying the light from these distant galaxies, Hubble noticed a subtle shift, a reddening, as though the light was stretched. It was not a flaw in the telescope, nor a trick of atmosphere. It was a sign. Through the lens of spectroscopy, light could speak, and in that speech lay motion. Every element had its fingerprint, a spectral signature. When those fingerprints shifted toward the red, it meant the source was moving away. Hubble began plotting the distances of galaxies against their redshifts. A simple graph, drawn by hand. Each point represented a world of hundreds of billions of suns. Slowly, a pattern emerged. The farther away a galaxy was, the faster it seemed to recede. It was not random. It was law-like, mathematical, undeniable. The universe was not static. It was expanding. This discovery was as breathtaking as it was incomprehensible. For centuries, the heavens had been thought eternal, immutable, a vast celestial clockwork set into motion by some prime mover, ticking in silence forever. The idea that the universe itself could grow, could stretch like fabric, contradicted everything science and philosophy had held sacred. Einstein himself had once resisted such an idea. When he formulated his general theory of relativity in 1915, his equations suggested a universe that could not remain still. Space, according to his mathematics, should either expand or contract. Troubled by this result, Einstein introduced a term, the cosmological constant, an invisible pressure designed to hold the universe in balance. He wanted harmony, not motion. But the universe had no such need. When Einstein visited Mount Wilson years later and saw Hubble's data, he reportedly murmured that omitting the possibility of expansion had been his greatest blunder. Whether the quote is legend or truth, the sentiment remains cosmic irony. Even the greatest mind of the 20th century had tried to keep the universe confined within human expectation, and failed. The implications were staggering. If the universe was expanding, then at some distant moment in the past, it must have been smaller. Go back far enough, and all galaxies, all matter, all energy would converge to a single point, a primordial moment of unimaginable density and heat. The idea would later evolve into what we now call the Big Bang. But in the 1920s, the thought of a universe with a beginning was heresy wrapped in mathematics. Astronomers struggled to accept it. The philosopher Arthur Eddington called the notion repugnant. The universe, he said, should be eternal. It had no beginning, and it would have no end. But the data refused to obey philosophy. Night after night, the galaxies whispered their retreat through the red lines of their light. Hubble's telescope became a time machine. Each faint glow in his photographic plates was a message from the past, light that had traveled millions of years across expanding space to reach his glass. The deeper he looked, the younger the universe appeared. The farther he reached, the faster it ran away. There was a poetic cruelty in it. To see the cosmos clearly was to witness it leaving. Each galaxy, a farewell note carried on the wind of spacetime. Humanity had finally looked beyond its home, only to find that everything else was fleeing. The Hooker telescope, with its grinding gears and polished mirrors, became a kind of oracle. Through it, the cosmos confessed its restlessness. The stars were no longer static candles in the firmament. They were passengers in an ever-widening sea. For millennia, humankind had asked what lay beyond the stars. Now the answer was almost unbearable. Everything lay beyond, and it was moving away. In the years that followed, astronomers raced to refine the measurements. Hubble's constant, the rate of expansion, became a new cosmic parameter. Yet, even as the number grew more precise, the meaning remained elusive. What could make the fabric of space itself stretch? No force was known to science that could do such a thing. The concept of expansion was not like an explosion, not matter flying outward into emptiness. There was no center, no edge. Rather, it was space itself that grew, carrying galaxies along like leaves on a rising tide. The universe did not expand into something. It expanded within itself. Every meter of the cosmos became a little larger with every passing moment. In this realization lay both beauty and existential dread. The same physics that allowed galaxies to drift apart also governed the atoms in our bodies. And yet, while cosmic space expanded, the forces that bound matter, gravity, electromagnetism, held us together. Humanity lived, and still lives, within a delicate balance between the vast and the intimate. When Hubble's findings reached the broader scientific world, disbelief gave way to revolution. A new vision of the cosmos emerged, not a static cathedral, but a living, breathing entity, dynamic and evolving. The universe was no longer a backdrop for existence. It was existence itself in motion. The stars, once symbols of permanence, were recast as evidence of change. The night sky was not eternal. It was a record of movement. Each point of light, each galaxy, was a traveler on an invisible current that had begun long before time had meaning. In that age of discovery, Hubble did not yet know what caused the expansion, nor what fate awaited it. He could not have imagined that decades later, scientists would find the expansion speeding up, defying every expectation of gravity. But he had opened the first door, the realization that the universe itself could evolve. From the quiet dome of Mount Wilson, under the thin air of the Californian mountains, humanity's perception of reality changed forever. The cosmos was not the serene painting we once imagined. It was alive, restless, and in motion. A vast organism of space and time, still unfolding. Einstein's equations, Leavitt's stars, Hubble's graphs, together, they formed a trinity of revelation. Mathematics gave form to the unseen, starlight gave it measure, and observation gave it truth. The expansion of the universe was not just a scientific discovery, it was a philosophical awakening. The realization that everything known and loved was part of a story still being written, a story of creation in progress, and somewhere in that story, between the whisper of redshift and the hum of cosmic background light, lies the most haunting truth of all. The universe is not done. It never was. It is still becoming. For the first time in history, humanity saw the cosmos not as a painting to be admired, but as a film, a moving image of creation unfolding in real time. Every night sky since then has carried the same secret, that the stars above are not still, and the universe beneath them is not calm. The discovery did not end with Hubble. It began there, with one man, one telescope, and a sky that refused to stand still. And as the dome of Mount Wilson closed that night, sealing away the echoes of the discovery, the world below remained unaware that the cosmos had just been set in motion. Forever. The night that changed everything did not come with thunder or revelation. It arrived in silence, beneath a dome of cold steel and colder stars. On that night, the universe itself seemed to whisper a confession, and for the first time in human history, science listened. The year was 1929. In the thin air of Mount Wilson, a small collection of glass plates had rewritten the cosmos. Dots of light, so faint they could barely be seen, were found to be fleeing, retreating across an ocean of darkness. The pattern was unmistakable. The farther a galaxy lay from Earth, the faster it was moving away. This was not motion through space. It was the motion of space. The very fabric of the cosmos, the invisible geometry that carried stars, gas, and time itself, was stretching. The universe was not still. It was alive. When Albert Einstein visited the Mount Wilson Observatory in the early 1930s, he was already the reluctant prophet of this truth. His own equations, written nearly 2 decades earlier, had whispered the same possibility. But he had silenced them. In 1917, Einstein's general theory of relativity had shown him that space and time were not passive backdrops. They were dynamic, able to bend, twist, and respond to matter and energy. Yet when he applied his theory to the cosmos, the result was disturbing. The equations demanded motion. The universe, by their logic, could not stand still. To counter this, Einstein inserted an artificial term, the cosmological constant, a subtle mathematical pressure designed to hold the universe in place. He had invented, in essence, a cosmic glue. He believed the heavens to be eternal, unchanging, perfect. To him, motion on such a grand scale was chaos. A universe in flux was a universe without meaning. But when Edwin Hubble's data reached him, the denial collapsed. Through the telescopes, the distant galaxies spoke a language his equations had already known. Their red-shifted light was not a trick, nor a misunderstanding. It was truth. The universe was expanding. Standing on Mount Wilson's windswept deck, Einstein peered into the dome and quietly accepted defeat, or perhaps revelation. He later called the cosmological constant his greatest blunder, though today, that same term may yet describe the force that drives the universe's expansion, what we now call dark energy. History, like space, has a strange sense of symmetry. In that single realization, the cosmos was reborn. The static universe, the eternal stage upon which creation once played its dramas, was gone. In its place stood a living, breathing expanse where time and space themselves evolved. Galaxies became travelers, stars became temporary, and the heavens, once a symbol of permanence, revealed themselves as motion frozen in light. This was not merely a discovery, it was a revolution, a shift so profound that it would redefine existence itself. From the quiet halls of Europe came a voice that had already predicted what Hubble and Einstein were only beginning to see. A Belgian priest and physicist, Georges Lemaitre, had been studying the same equations years before. In 1927, he proposed something radical, that the expansion implied an origin. If the galaxies were moving away, then once, long ago, they must have been closer together. Trace the motion backward, and all of space, all of time, all of energy must converge to a single point, a primeval atom, as he called it, a beginning not of stars or planets, but of existence itself. To Lemaitre, the universe was not eternal. It had a birth. The cosmos, vast and ancient as it seemed, had once been smaller than a grain of sand. compressed beyond imagination, filled with the energy that would one day become everything. It was an idea so immense that even those who believed in infinity struggled to face it. When he presented his theory, many scientists dismissed it outright. They mocked it as the fireworks beginning, a philosophical intrusion into physics. Some argued that a finite beginning was too close to religious thought, too unscientific to be trusted. Others, like the great astronomer Fred Hoyle, would later propose an alternative, a steady-state universe, one that eternally created new matter to fill the void left by expansion, avoiding the discomfort of a cosmic birth. But time and evidence would side with Lemaitre. The emotional impact of this revelation was far greater than science alone could measure. For centuries, humanity had drawn comfort from the notion of a timeless cosmos, an eternal sky beneath, which civilizations rose and fell, but the stars remained unmoved. Now, that illusion was shattered. The stars were no longer eternal beacons. They were burning stories, born, aging, and destined to fade. The sky had become a history book written in light, its pages expanding ever outward. To look at the universe now was to look into the past. Each photon a messenger from an earlier age, each redshifted glow a fading echo of what once was. In that realization came both awe and sorrow. The universe was no longer a perfect clock. It was a growing organism. And like all living things, it had a beginning. In the decades that followed, cosmology transformed from speculation into precision. New observations confirmed that galaxies truly did recede from one another, carried by the expansion of space-time itself. The concept of an evolving universe became the cornerstone of modern science. For the first time, humanity possessed not just a universe to observe, but a universe with a story, a past, a present, and a possible end. Physicists began to ask deeper questions. If the cosmos was once smaller and denser, what was it like in its earliest moments? What forces shaped its rapid inflation, its cooling, its structure? And if the universe had a beginning, could it also have an end? But beneath the equations and theories, something deeper stirred, a quiet existential unease. The death of the static cosmos was not just a scientific shift, it was a philosophical one. The heavens, once thought to embody permanence and perfection, were now seen as transient, evolving, and fragile. In a single generation, humanity had gone from believing it lived at the center of a fixed creation to realizing it drifted in an expanding void. One galaxy among trillions. It was both humbling and terrifying. Einstein, who had sought elegance in the laws of nature, now found himself staring at a universe that would not stay still. The geometry of space-time was restless, an infinite fabric that could stretch, curve, and warp like the surface of an ocean. Every star, every planet, every being that ever lived would one day be carried apart by that same expansion. The grand clockwork of Newton had been replaced by a symphony of flux. Lemaitre's primeval atom would eventually evolve into what we now call the Big Bang Theory, a name first used mockingly by Hoyle during a BBC radio broadcast in 1949. But the mockery could not undo the truth. Over time, evidence accumulated. The cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies, all spoke of a universe born from fire. Lemaitre had been right. The cosmos had not always been as it is now. The galaxies were not eternal. They were travelers, carried outward by a space that itself was expanding. The universe was, in the truest sense, in motion. And yet, within that motion lies a strange harmony. As space stretches, galaxies recede, but locally, within the gravitational embrace of clusters and stars, the bonds hold. Gravity resists the flow, stitching islands of order within an expanding sea. It is this tension between motion and stillness, between the infinite and the intimate, that gives the universe its structure. To exist, even briefly, is to live in the balance between those two forces, the pull of gravity and the push of expansion. Every atom in every living being is part of this vast negotiation. The cosmos grows, and we grow within it. By the mid-20th century, the vision of a dynamic universe had become the foundation of modern physics. The ancient dream of a static cosmos had died, but in its death, a greater wonder was born, the knowledge that we live inside a story still unfolding. Each galaxy's flight is a sentence written in the grammar of space-time. Each photon that reaches our telescopes is a syllable of light, telling us where the universe has been and where it is going. We no longer see the sky as a ceiling. It is an ocean without shore, expanding, deepening, and changing. And as night falls across the observatories of the world, the same truth still hums through the instruments, through the silent mirrors pointed skyward. The universe is not what it was yesterday. Every second, every heartbeat, the distances grow. The galaxies drift apart. The wavelengths stretch. The cosmos exhales. In that eternal breath lies the memory of its birth and the promise of its future. The static universe is gone, its stillness buried beneath the tide of time. In its place, there is motion, creation, and transformation without end. And in the faint red light of receding galaxies, the cosmos whispers the same truth it first revealed to Hubble and Einstein under the mountain sky, that everything we see is part of a grand unfolding, a universe not made to last, but made to move. There are moments in science when the universe seems to whisper back, faintly, through static and silence. The year is 1964. High above the gentle hills of Holmdel, New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, stand beside a massive white horn antenna. It was built for satellite communication, not for cosmic revelation. And yet, hidden within its steel frame, a secret waited that had traveled across nearly 14 billion years of time. Every day, they hear it, a soft, persistent hiss. Static, that lingers no matter which direction the antenna turns. They blame the equipment, the atmosphere, even the pigeons that had nested inside the great horn. But nothing silences the sound. The noise is not of Earth. It is not of any star or galaxy. It is older than light itself. When Penzias and Wilson finally report their findings, they unknowingly confirm what theorists had long suspected. The faint radiation pervading every inch of the sky was the dying warmth of the universe's own birth, the cosmic microwave background, the afterglow of creation. In that instant, the story of the cosmos changed forever. The static became a voice. The silence of the heavens became a memory of their origin. Decades earlier, the seeds of this revelation had already been planted. In the 1940s, physicist George Gamow, along with Ralph Alpha and Robert Herman, had predicted that if the universe began in a hot, dense fireball, then its ancient light should still linger. Stretched and cooled by billions of years of expansion, it would fill space not as visible light, but as a faint, uniform glow in the microwave spectrum, a relic temperature just a few degrees above absolute zero. For years, their prediction lay buried in academic papers, untested, unsearched for. The idea seemed too speculative, the technology too crude. The scientific world still debated whether the cosmos had truly begun with a bang, or whether it had always been eternal, unchanging, a steady state. But nature keeps its records, even when humanity forgets where to look. When the discovery of the CMB reached the scientific community, it was as though the universe itself had spoken in confirmation. That faint hiss was not noise. It was a message written in radiation, encoded in the very structure of space-time. Every direction revealed the same temperature, about 2.7 Kelvin, nearly uniform, save for minute variations of 1 part in 100,000. These tiny ripples, these delicate imbalances, would later be seen as the seeds from which galaxies, stars, and planets would form. Within those fluctuations lay the blueprint of all cosmic structure. The Big Bang was no longer theory. It had become evidence, tangible, measurable, eternal. What Penzias and Wilson had heard was not just static. It was the first light, redshifted by cosmic expansion, smoothed and stretched until it wrapped around the entire sky. The radiation came from a time when the universe was only 380,000 years old, when matter and light first parted ways. Before that, the cosmos was a blinding plasma, opaque and chaotic, where atoms could not yet exist. Then came the moment of release, recombination. When electrons joined protons to form the first hydrogen atoms, light broke free, racing outward in all directions. That same light still travels, reaching Earth billions of years later as the faint microwave glow of creation. In this discovery, humanity glimpsed not only its origins, but its own smallness within the great unfolding of time. The night sky, once seen as silent and eternal, was revealed to be alive, an echo chamber of ancient fire. The cosmic microwave background became a window to the past, allowing scientists to reconstruct the earliest seconds of existence. Space telescopes like COBE, WMAP, and later Planck mapped the subtle patterns in that radiation with exquisite precision. They found tiny temperature differences, mere microkelvins, tracing the cosmic scaffolding upon which galaxies would later form. These maps became the most detailed portraits ever made of the infant universe, snapshots of time itself, frozen at the dawn of creation. Each point of light spoke of an age when the universe was young, when matter and energy were still learning to dance in rhythm. But the cosmic echo did more than confirm a theory. It deepened the mystery. If the universe began in a hot, dense state, what caused it to expand? Why did it grow so fast, so evenly, across distances far greater than light could have traveled? To answer that, scientists looked deeper into the fabric of those first moments, beyond the Big Bang itself, into what might have come before. In the 1980s, physicist Alan Guth proposed a radical idea: cosmic inflation. In the earliest trillionth of a second, the universe, he said, underwent an unimaginable burst of expansion, growing exponentially faster than the speed of light. Space itself ballooned, stretching quantum fluctuations into the vast structures of galaxies and clusters seen today. Inflation explained the smoothness of the CMB, the uniformity of temperature across billions of light years. It described how something infinitely small could give birth to something unimaginably large. Yet even inflation left questions untouched. What triggered it? What ended it? And what, if anything, came before? The CMB became the silent witness to all of it, the fossilized light of a universe in transformation. When viewed with sensitive instruments, it appears not as a smooth field, but as a cosmic tapestry, a delicate mottling of blues and reds, each color marking tiny variations in temperature and density. Those ripples are the fingerprints of creation, etched across the heavens. They tell a story written long before stars burned, long before matter congealed, long before time moved as we know it. They tell of a universe that once was pure energy, a storm of photons and particles, colliding, annihilating, creating anew. They tell of gravity's first whispers, of the birth of structure, of light's first freedom. And in their symmetry lies something hauntingly beautiful, a reminder that everything, from galaxies to life itself, is woven from the same cosmic fabric that once glowed with the heat of existence. For humanity, this revelation was both humbling and transcendent. The heavens had spoken in radiation, not words, yet the message was clear. The universe had a beginning, and thus, a story. No longer could the cosmos be seen as eternal and unchanging. It was an evolving entity, with a past, a present, and perhaps a future written in expansion. The steady-state universe, once favored by minds like Fred Hoyle, faded into history. The Bang, he had once mocked in name, became the most enduring symbol of modern cosmology. From that faint hiss of microwaves emerged an entire narrative of cosmic evolution. Stars, galaxies, and clusters became chapters in a story billions of years long. The echo of the Big Bang was the universe's own autobiography, spoken across time. Today, The cosmic microwave background remains one of the most studied signals in science. Each refinement of measurement brings new insight into dark matter, dark energy, and the very curvature of space-time itself. The CMB's near-perfect uniformity suggests that the cosmos is flat on the largest scales, neither closed like a sphere nor open like a saddle, but balanced at the edge of geometry. Yet, within its faint irregularities lies the whisper of deeper truths, of unseen forces, of hidden matter shaping the growth of galaxies. Some speculate that inflation was not a singular event, but part of an infinite series, a multiverse of expanding bubbles, each with its own physics, its own fate. If true, our universe may be but one note in an endless cosmic symphony, and still, the CMB continues to sing, a chorus of photons older than the first stars, older than time as we understand it. In its quiet hum, there is something deeply human, the yearning to understand, to listen, to find meaning in the noise. For every atom in the body was once part of that early light. Every element that makes up earth, life, and thought was born in the furnaces that followed, forged from the echoes of that same primordial blaze. The radiation that Penzias and Wilson detected was not only the afterglow of creation, it was the ancestor of every sunrise, every star, every spark of consciousness that would ever look back upon the sky and ask where it all began. In the grand silence of the cosmos, that faint background hum continues, eternal, patient, unwavering. It is the most ancient sound the universe has ever made, a whisper that carries the memory of time's first breath. And though it fades, it never ends. For as long as the universe expands, that light will stretch and cool, its wavelength growing, longer, its voice softer, a song receding into the infinite. But in every echo, it tells the same story, that from darkness came light, from stillness came motion, and from silence came everything. Across the silent abyss, galaxies drift like lanterns on a dark cosmic ocean, each one a whisper of light receding, fleeing. Nearly a century after Hubble's revelation that the universe was expanding, humanity turned its telescopes toward the depths, not merely to watch the heavens, but to chart them, to map the shape of everything, from the mountain peaks of Chile to the frozen deserts of the South Pole, from orbiting observatories to vast mirrors buried beneath the night. Astronomers began their grand cartography of the cosmos. It was no longer enough to know that galaxies moved apart. The question had changed. How did they move? Where were they going? And what invisible hands sculpted their flight? In the 1990s, a single image changed astronomy forever. The Hubble Deep Field, a patch of sky no larger than a grain of sand held at arm's length, was aimed at for 10 days of continuous exposure. What emerged from the darkness stunned the world. Within that tiny corner of emptiness lay over 3,000 galaxies, each containing billions of stars, each drifting farther away into the sea of space. The universe, once thought vast beyond measure, was revealed to be far vaster still. Not an endless void, but an intricate tapestry of light and motion. And as the images multiplied, so did the mystery. The Sloan Digital Sky Survey, launched in the early 2000s, became humanity's most ambitious cosmic census. Night after night, its telescopes scanned the heavens, gathering light from millions of galaxies across billions of light years. What emerged from its data was not chaos, but structure. Galaxies did not scatter randomly. They formed colossal networks, filaments stretching across hundreds of millions of light years, weaving a delicate cosmic web. Between these filaments yawned vast voids, empty realms where galaxies were rare and darkness reigned. Like dew on a spider's web, the universe shimmered with strands of matter bound together by the quiet pull of gravity. And something more elusive, dark matter. It was as if the cosmos were frozen mid-breath, its form suspended between expansion and collapse, held together by forces both seen and unseen. This great cosmic architecture, this web of galaxies and emptiness, told a story written by gravity over eons. Where matter was slightly denser, it drew in more matter, forming galaxies and clusters. Where it was thinner, space hollowed out, birthing the cosmic voids that now span hundreds of millions of light years. The universe, then, was not expanding like an inflating balloon, smooth and uniform. It was a living structure, stretched, warped, and sculpted by the invisible hands of physics. Dark matter, though unseen, dictated its design. It made up nearly 85% of the total mass of the cosmos, yet emitted no light, no signal, no hint of its nature. Only through its gravity could it be traced, through the bending of light, the clustering of galaxies, the silent shaping of cosmic filaments. If ordinary matter was the paint, dark matter was the canvas upon which the universe was drawn. But within this grand cosmic web, astronomers noticed something deeply unsettling. When they measured the rate of expansion, the so-called Hubble constant, their answers refused to agree. Two methods, both grounded in precision, both seemingly reliable, yielded conflicting results. One looked near, measuring the light of Cepheid variables and type IR supernovae within nearby galaxies, using the same cosmic yardsticks that Hubble himself once used. This gave a higher value. The universe, it seemed, was expanding faster than expected. The other looked far, analyzing the patterns imprinted in the cosmic microwave background, the ancient afterglow of the Big Bang itself. These measurements, made by satellites like Planck, told a slower story, an older, more measured universe. The two answers differed by nearly 10%, a small number, yet vast enough to shake the foundations of cosmology. This growing disagreement became known as the Hubble tension. To some, it was merely an error, a flaw in the instruments, a misunderstanding of the data. But as the measurements became more refined, the gap refused to close. Perhaps, scientists began to whisper, the tension was not an error at all, but a clue. A clue that something deeper was at play, something that the equations of Einstein and the models of modern cosmology could not yet grasp. The mystery drew attention from every corner of theoretical physics. Could dark energy, the enigmatic force driving cosmic acceleration, be changing with time, evolving like a living field? Could dark matter interact in ways yet unseen, subtly altering the expansion history of the cosmos? Or perhaps the universe was not isotropic at all. Perhaps at scales beyond human observation. It expanded unevenly, faster in some directions than others. Some even dared to suggest that the cosmological principle, the assumption that the universe looks the same everywhere, might be an illusion born of our limited perspective. Each theory offered an explanation, and yet none felt complete. It was as if the universe, when looked at too closely, blurred at the edges, as though reality itself resisted being fully mapped. The cosmic web, thus, became both a triumph and a riddle, a grand design that hinted at hidden dimensions of understanding. Through instruments like the Dark Energy Survey and the James Webb Space Telescope, humanity now peers deeper into that web, tracing how galaxies formed and evolved across cosmic time. Each new image reveals structures more intricate, more alive than imagined. Great filaments bend under the weight of unseen mass. Galaxies move like dust in a current too vast to comprehend. And between them, silence. The voids are not empty, but waiting. Their darkness may yet hold the keys to physics unimagined. To map the universe is to map time itself. Every photon that reaches Earth carries the memory of a journey billions of years long. Looking outward is to look backward. Each distant galaxy a snapshot from a younger cosmos. The maps drawn today are not static charts. They are moving tapestries, frozen frames of an ongoing expansion that began in the first fraction of a second after creation. The farther we look, the more we see the universe not as a place but as an event, still unfolding, still escaping comprehension. Amidst this pursuit lies a haunting irony. The more precise the measurements become, the less the cosmos seems to make sense. The numbers, the patterns, the constants that once offered certainty now give rise to contradictions. The closer scientists approach truth, the more it seems to retreat, like the edge of a receding horizon. The Hubble tension is more than a numerical puzzle. It is a philosophical one. It whispers that perhaps the fabric of reality is not yet fully known, that our understanding of space-time, gravity, and cosmic history remains incomplete. Perhaps the very laws that govern the universe have shifted across epochs, or bend subtly under conditions beyond human reach. Perhaps the constant that defines expansion is not constant at all, but alive, evolving with the universe itself. In laboratories and observatories around the world, the search continues. Teams at NASA, ESA, and countless research institutions refine their instruments, seeking ever fainter signals. Space telescopes like Euclid and upcoming missions like Nancy Grace Roman aim to measure cosmic acceleration with unprecedented precision. They hunt not just for answers, but for the boundaries of ignorance, the edges of human perception. Every new data point, every refined constant, brings the cosmos into sharper focus, and yet, simultaneously, pushes the mystery deeper. To chart a universe that is running away is a paradox in itself. Every measurement, every observation, is made from within a world that moves too, a drifting island of stars adrift in an ocean of expanding space-time. The galaxies seen today are not where they once were. Their light left them billions of years ago, and by now, they have fled to distances unimaginable. To map the cosmos, then, is to draw the shadow of a moving wave. It is to sketch the echo of a moment long vanished, and yet, from these echoes, humanity continues to piece together the grand mosaic, an ever-changing map of the fleeing universe. In this pursuit, one truth remains constant. The universe is not still. It breathes, it stretches, it evolves. It is a living cosmos, dynamic, unpredictable, filled with tension and wonder. Every filament, every void, every distant galaxy speaks of a balance between chaos and order, between what is known and what is yet to be. And though humanity's maps grow ever more detailed, they remain incomplete, because the universe itself is incomplete, still expanding into tomorrow. At the end of each night's observation, when the telescopes close their eyes to dawn, the data speaks in silence. It tells of a universe still in motion, of galaxies racing into the dark, of structures too vast for language, too elegant for chance. And somewhere between those fleeing lights and the endless void lies the echo of a question older than time. Is the universe expanding into emptiness, or into something beyond understanding? The deeper humanity looks, the more the cosmos resists final answers. The farther it maps, the less it seems to know, for perhaps in its fleeing, the universe is not running away at all, but leading us onward into mystery. For most of the 20th century, cosmology moved with quiet confidence. The universe, though expanding, was thought to be obeying gravity's inevitable pull, slowing, coasting, destined one day to stop and perhaps fall back upon itself. A cosmic breath drawn and released, a grand cycle of birth and return. But in the closing years of the 20th century, that certainty began to tremble, and in 1998, it shattered. The story began with light, faint flickers from dying stars, type Ia supernovae, scattered across the distant cosmos. They were chosen not for their beauty, but for their reliability. These stellar explosions burned with near-perfect uniformity, releasing the same amount of light wherever they occurred. To the astronomers who studied them, they were more than spectacles. They were cosmic yardsticks. Two teams set out to measure the universe with these celestial candles. One, led by Saul Perlmutter in California, called itself the Supernova Cosmology Project. The other, led by Brian Schmidt and Adam Rees, operated half a world away. The High-Z Supernova Search Team. They were rivals. Both sought to answer a single ancient question: how fast is the universe slowing down? At that time, the answer was assumed to lie between two fates: an open universe, expanding forever, but gradually fading into darkness, or a closed one, destined to collapse in a fiery end. No one imagined a third possibility. The teams observed dozens of distant supernovae, their light stretched and reddened by the expansion of space itself. By comparing their apparent brightness to their redshift, astronomers could calculate both their distance and the speed at which the universe had expanded since they exploded. Each data point was a window into the past, a snapshot of the cosmos billions of years ago. But as the results came in, the pattern defied everything the equations had promised. The distant supernovae were dimmer than they should have been, not because they were weak, but because they were farther away than expected. This meant that the expansion of the universe had not been slowing down, it had been speeding up. For weeks, both teams rechecked their data. They recalibrated instruments, reviewed light curves, reanalyzed spectra. Surely there had been an error, a smudge on the lens of the cosmos. But the evidence remained. The farther the galaxy, the faster it was receding, not through momentum, but through something unseen, something driving the expansion itself. It was a result so strange, so radical, that one scientist described it as a discovery we didn't want to believe. Yet reality does not ask for belief. It only asks to be seen. The announcement came quietly in late 1998. Both groups had reached the same conclusion. The universe was not coasting. It was accelerating. This moment, invisible to most, unimaginable to all, marked the death of an era in cosmology. For centuries, gravity had been seen as the master architect of the universe, the great sculptor of motion, the shaper of stars and galaxies. But now, something had appeared that opposed it, a force not of attraction, but of repulsion, a mysterious pressure woven into the very fabric of space-time, pushing galaxies apart. It was as though the universe itself had changed its mind, deciding not to fade, but to flee. What could possibly cause such an effect? What hidden energy could counteract gravity on the scale of the cosmos itself? Scientists searched history for clues, and there, buried in the equations of general relativity, they found one, Einstein's cosmological constant. In 1917, Einstein had added this term, denoted by the Greek letter L, lambda, to his field equations. At the time, he believed the universe must be static. His equations, without adjustment, predicted that the cosmos should expand or contract. To correct this, he introduced L as a gentle, opposing force, a mathematical anti-gravity to hold the universe still. But when Hubble later discovered cosmic expansion, Einstein abandoned the idea, calling it his greatest blunder. For decades, L was forgotten. Now, in the light of the supernovae, it returned. Perhaps Einstein's blunder was not a mistake at all, but a premonition. The cosmological constant was reborn, but with a new identity. It was no longer a fudge factor, but a profound mystery. Physicists gave it a new name, dark energy. It would become the most dominant component of the universe, accounting for nearly 70% of its total energy density. Yet no one knew what it was. Was it an inherent property of space itself? An energy of the vacuum? A whisper of quantum fields forever bubbling at microscopic scales? Or was it something entirely different? A new, unknown force field permeating the cosmos? If space could stretch, could it also want to stretch? Was expansion not a motion, but a natural expression of existence itself? The discovery sent shockwaves through physics. It meant that the fate of the cosmos was not to fall back into itself, but to drift further apart, faster and faster, until the night sky grows dark again, as galaxies race beyond the reach of light. In the distant future, the stars themselves will fade, the cosmic web will unravel, and all that remains will be the silent expansion of emptiness. A universe that should be fading, instead races into the void. In laboratories across the world, scientists began to probe this cosmic enigma. Could quantum fluctuations, the brief appearance and disappearance of virtual particles, account for this mysterious energy? The calculations were staggering. Quantum field theory predicted a vacuum energy 120 times stronger than what was observed. It was and remains the most catastrophic mismatch between theory and measurement in all of science. If dark energy truly exists as vacuum energy, then reality itself is finely tuned beyond comprehension, delicately balanced between everything and nothing. Others proposed more radical ideas. Perhaps Einstein's equations were incomplete. Perhaps gravity itself behaves differently across cosmic distances. In modified gravity models, space-time might curve in unfamiliar ways, creating the illusion of acceleration without any actual dark energy. Still others turned to the early universe for answers. Could the same mysterious field that inflated the cosmos moments after the Big Bang still linger, weak but eternal? Could we be living in the afterglow of cosmic inflation? A relic field that continues to stretch the fabric of space even now. Every possibility led deeper into the unknown. Each hypothesis illuminated a different facet of the same mystery. Why does the universe expand? And why does it want to expand faster? The discovery of acceleration did not merely reshape cosmology, it reshaped philosophy. For the first time, humanity glimpsed a universe not balanced between creation and destruction, but destined for eternal dispersal. a cosmos where energy does not fade evenly into the night, but grows stronger in its emptiness. Every galaxy, every star, every atom is part of this grand escape, a motion that began before time, and will not end even when time itself dissolves. The equations of general relativity, when combined with the observed acceleration, suggest an outcome both magnificent and terrifying. The cosmos will continue to expand forever, cooling, dimming, until even the last photons stretch into oblivion. It is the slow death of light, the ultimate silence. And yet, even in this bleak horizon, there is wonder. For in its flight, the universe has given birth to consciousness capable of noticing it. Beings who can look into the void and name its mysteries. Perhaps dark energy is not a curse, but a clue. Perhaps the expansion is not chaos, but design. The unfolding of a cosmic story still being written. Einstein's constant, Hubble's motion, and Perlmutter's light. All pieces of a single question that still burns through the night sky. Why is the universe expanding at all? And what does it mean that the expansion never ends? When Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011, the world honored more than their discovery. It honored a revelation that changed humanity's view of existence itself. The universe was no longer a clock winding down. It was a fire growing colder, yet ever brighter in its reach. An infinite expansion, driven by an invisible hand. Somewhere, beyond every galaxy, beyond the last particle of light, the unknown still unfolds, silent, powerful, eternal. And as it does, the stars drift farther, the darkness deepens, and space itself accelerates into nothingness, leaving only the echo of a question that may never end. What is the force that drives creation away from itself? Beneath the vast, silent fabric of space, there lingers a mystery that defies comprehension, a force unseen, yet relentless, reshaping the fate of the cosmos itself. Astronomers gave it a name, dark energy. But a name, they soon realized, is not an understanding. It is merely a label placed upon the edge of human ignorance. The story begins with a paradox. When the universe was found to be accelerating, scientists turned again to an idea once abandoned, Einstein's cosmological constant. The symbol L, simple, elegant, re-emerged as a possible key. In this interpretation, every cubic meter of space contains a small, uniform energy. Empty space, it seemed, was not truly empty. The vacuum itself might possess weight, a subtle pressure that pushes galaxies apart. But in the quantum realm, that idea explodes into absurdity. According to quantum field theory, the vacuum should teem with energy. Virtual particles flickering into existence and vanishing again in an instant. If all those fluctuations are summed, the total vacuum energy should be immense. So immense that the universe would have torn itself apart in the first instant of its birth. Yet, the observed value of dark energy is unimaginably smaller. Smaller by a factor of 10 to 120. The largest discrepancy between theory and observation in all of physics. In the equations, the numbers collapse beneath their own infinity, and so began the search for alternatives. Perhaps dark energy is not constant at all. Perhaps it is alive, an evolving field, dynamic and restless, changing its strength over cosmic time. This idea, called quintessence, imagines a hidden energy that seeps through the universe like an invisible wind, waxing and waning as galaxies drift farther apart. In this model, dark energy is not a fixed property of the vacuum, but a fluid presence, a ghostly ocean swelling beneath the surface of spacetime itself. Yet even this raises new questions. If dark energy can evolve, what governs its rhythm? What particle carries its force? What law of nature sustains its reach across billions of light years? Some scientists turn their eyes toward gravity itself. Perhaps Einstein's theory, magnificent though it is, falters on scales as vast as the cosmos. Maybe space is not merely curved by matter. Maybe it bends in response to something deeper. Modified gravity theories like FR models or massive gravity attempt to rewrite the geometry of the universe, allowing cosmic acceleration to emerge not from an unseen energy, but from the very structure of spacetime. But each solution leads to another paradox, a new door that opens only onto a darker corridor. The cosmological constant explains the observations, but not the numbers. Quintessence breathes life into theory, but no evidence of its field has yet been found. Modified gravity offers elegance, but breaks the harmony of general relativity, a theory confirmed to exquisite precision. The result is a silence that feels almost cosmic. Humanity holds the equations, the telescopes, the data, yet the meaning slips through like light through mist. Even the most advanced probes, the Planck satellite, the Dark Energy Survey, the Euclid mission, can only map the consequences of this force, never its essence. They trace how galaxies drift, how cosmic filaments stretch, how ancient light is distorted by the accelerating fabric. But the hand that drives it all remains unseen. In the darkness between galaxies, there is no sound, no color, no signal, only the faint pulse of expansion, growing faster with every billion years. It is as if the universe itself is being lifted outward by an invisible tide, drawn toward a horizon it can never reach. Some physicists whisper that dark energy may not even exist, that the acceleration is an illusion born from our limited perspective. Others suspect the universe could one day change its mind, that dark energy might decay, reversing its push, leading all of creation back into collapse. But for now, the cosmos drifts outward, ever faster. The galaxies recede like fading embers, carried by a wind without origin, without sound. And in this expanding void, humanity stands with an empty hand, aware enough to know that something is there, yet powerless to define it. A force that fills all of space and yet escapes all understanding. A silence older than time, named only so that we might speak of it. Dark energy, a symbol not of what is known, but of what remains hidden. A question written across the sky, and the echo of our own ignorance, expanding with the universe itself. In the silence between galaxies, in the unlit regions where no atom drifts, there exists something that should not exist at all. Motion within stillness. For even in the deepest void, emptiness is an illusion. According to quantum field theory, space itself is alive. Beneath the calm fabric of the cosmos, an invisible storm brews, a restless sea of creation and annihilation. Virtual particles, flickering in and out of existence, erupt from nothingness, collide and vanish again before they can be seen. Every point in space becomes a theater of chaos, where energy is borrowed from the void and then returned to it in the next breath of time. This phenomenon is known as vacuum energy, the energy of nothing. But in the equations that govern quantum fields, nothing is not the absence of being. It is a state of eternal fluctuation, a storm that never stops. The uncertainty principle, written by Heisenberg nearly a century ago, decrees that even perfect emptiness cannot remain still. Energy and time are bound by a law of unrest. The shorter the moment, the greater the disturbance within it. In that trembling vacuum, the seeds of creation and destruction coexist. Every atom, every star, every galaxy is built atop that seething, invisible ocean. But this vision of a living void comes with a terrible paradox. When physicists attempt to calculate the total energy of that quantum sea, summing every vibration, every flicker of every possible field, the result is monstrous. The predicted energy density of the vacuum is 10 to 120 times larger than what the universe actually displays. If the quantum vacuum truly carried such force, the expansion of space would have been so violent that galaxies, atoms, even the laws of physics themselves could never have formed. The universe would have ripped apart before it began. This chasm, the vacuum catastrophe, stands as the greatest mismatch between theory and observation in the history of science. It is as if the equations themselves, when peering into the abyss, lose their meaning. Einstein's smooth spacetime, the elegant geometry that describes the bending of gravity, collides headlong with the quantum world's trembling uncertainty. In one, space is continuous, calm, and predictable. In the other, it is fractured, alive, unpredictable. Between them lies a conflict at the heart of modern physics, the war between general relativity and quantum mechanics. The universe appears to obey both, yet unites neither. Could this restless vacuum be the source of cosmic acceleration? Could the same fluctuations that whisper between particles also be pushing galaxies apart, stretching space-time itself? If so, the force driving the universe outward is not something separate from the void. It is the void, the same nothingness that fills interstellar space, might be gently prying the cosmos open, one infinitesimal instant at a time. But the scale of this phenomenon makes it almost incomprehensible. Quantum fluctuations occur over distances smaller than an atom, in timeframes shorter than a trillionth of a second. Cosmic expansion unfolds over billions of years, across distances greater than the observable universe. To connect these two extremes, the smallest and the largest, is to bridge a divide no human theory has yet crossed. Some physicists imagine the vacuum as a vast symphony, a trillion invisible notes resonating through the quantum fields that compose all of reality. Each fluctuation, each vibration contributes to the fabric of space-time itself. But why this song is so faint, why its power is almost entirely muted, remains one of the universe's deepest mysteries. Others suggest that the true vacuum may not be the ground state of nature, but merely a temporary lull, a false calm before a cosmic transformation. If that were true, the universe we know may not be stable at all. One day, a fluctuation could trigger a transition to a deeper vacuum, rewriting the laws of physics in an instant, a silent phase change that would end all known matter without warning. In that haunting possibility lies the echo of our ignorance. We can detect the pulse of the vacuum, but not its heart. We can name its effects, but not its origin. In the laboratories of Earth, quantum fluctuations reveal themselves faintly. In the Casimir effect, where two mirrors, placed close together in a vacuum, are drawn inward by invisible forces. In that tiny attraction lies evidence that the vacuum breathes, that the emptiness between those mirrors is not truly empty. And yet, scaling this phenomenon to the entire universe defies reason. The cosmic void appears to push, not pull, to drive matter outward, not draw it in. Somewhere between the microscopic dance of quantum foam and the grand curvature of cosmic space, something shifts direction, from attraction to repulsion, from gravity to expansion. No theory fully explains why. Perhaps the vacuum energy is not a single, constant pressure, but a field that interacts with the geometry of space-time itself. Perhaps the void is not uniform, but textured, its fluctuations not random, but patterned across scales we cannot yet perceive. Or perhaps the very concept of energy, in this context, breaks down, a human construct stretched too far into the unobservable. In the end, the mystery remains suspended in silence. The universe expands, carried by an invisible pressure whose source lies beneath the threshold of existence itself. In that silence, one truth resonates like the faintest heartbeat in a cosmic void. The void is not still. The emptiness of space is alive. The vacuum breathes, but we do not know its rhythm. In the beginning, there was silence, but not stillness. A fraction of a second after time itself was born, the universe is believed to have undergone a transformation so violent, so incomprehensibly fast, that it stretched the very meaning of beginning. This moment is known as cosmic inflation, the flash of expansion that shaped everything that would ever exist. In the late 1970s, a young physicist named Alan Guth sat before his chalkboard at the Massachusetts Institute of Technology, searching for answers to puzzles left unsolved by the Big Bang theory. Why was the cosmos so uniform, the same temperature and density in every direction? Why did space appear geometrically flat, when random expansion should have left it curved and uneven? And why did magnetic relics of the early universe, predicted by theory, simply not exist? The equations seem to whisper that something extraordinary had happened before the Big Bang as we understand it, a fleeting moment when the universe inflated faster than the speed of light. According to Guth's model, the young cosmos existed in a peculiar state, not quite stable, not quite chaotic, a false vacuum. In this state, space itself was saturated with enormous energy, a field trapped atop a potential hill, waiting to fall. But before it could, that trapped energy caused space-time to balloon exponentially. In less than a trillionth of a second, the universe expanded by an unimaginable factor, smoothing its wrinkles, flattening its geometry, and scattering quantum fluctuations like seeds across the newborn cosmos. Those seeds would later become galaxies, stars, and planets, and perhaps even life. When the false vacuum finally decayed into a lower energy state, the energy released ignited the Big Bang, heating the universe and flooding it with radiation. Inflation, in essence, set the stage upon which creation would unfold. Yet Goethe's theory carried implications far beyond what even he imagined. If inflation could begin once, could it not begin again, elsewhere? Physicists soon realized that inflation, as described by the equations, does not necessarily end everywhere at once. While our region of space may have cooled and settled into stability, other regions might still be inflating, expanding eternally, birthing new pockets of spacetime that blossom like cosmic bubbles. This gives rise to one of the most daring concepts in all of modern cosmology, the multiverse. In this vision, our universe is not unique. It is one bubble among countless others, drifting in a vast and endless sea of creation. Each bubble may have its own laws of physics, its own constants, its own rhythm of time. Some might collapse instantly. Others might bloom into universes rich with galaxies and life. We may never see beyond our bubble. The boundary of our cosmic horizon, the limit of what light can reach, is the edge of our observable story. Beyond it, if the multiverse exists, lies an infinity of untold tales. In this eternal inflation, new universes are constantly born from the decaying false vacuum, like sparks flickering from an endless fire. The cosmic landscape becomes not a single universe, but a multiverse, a self-replicating expanse where creation never ceases. But with this realization comes a quiet unease. If countless universes exist, each with its own version of physics, what meaning remains in the word why? Why does our universe have the precise conditions to allow life or thought at all? Is it the product of design, chance, or inevitability within an infinite cosmic lottery? Inflation does not answer that question. It only widens it. The concept of the false vacuum also introduces a haunting uncertainty. If our universe began within such a state, could it still be in one now, metastable, balanced delicately on an energy plateau? If so, a single quantum fluctuation, somewhere in the vastness, could cause it to collapse into a lower vacuum, a new state of reality with different physical laws. The transition would expand outward at the speed of light, rewriting existence in an instant. No warning, no resistance, just silence. The idea is not science fiction. It arises naturally from the mathematics of quantum fields. The Higgs field, discovered in 2012 at CERN, could hold the key. Current measurements of the Higgs boson's mass and interactions suggest that our vacuum may not be perfectly stable, only long-lived. A fragile equilibrium in a restless sea. If true, the same mechanism that once birthed the universe could one day end it. And yet, despite its ominous beauty, the theory of inflation has stood resilient against decades of scrutiny. Observations of the cosmic microwave background, measured by missions like COBE, WMAP, and Planck, reveal tiny variations in temperature that align precisely with inflationary predictions. Those subtle ripples in the ancient radiation, just 1 part in 100,000, are the fingerprints of quantum fluctuations stretched to cosmic scales by inflation itself. Still, inflation remains a model that touches the edge of what is knowable. It describes what may have happened, but not why. It maps the mechanics of creation, but not its origin. If inflation is eternal, then creation is not a singular event. It is an ongoing process without beginning or end. Somewhere, right now, new universes may be blooming, hidden beyond the reach of any light that will ever touch ours. In that infinite expanse, the question of why the universe expands may lose its meaning. Perhaps there was never a why, only a how. Perhaps the universe expands not for a reason, but because expansion is what existence does. It is the nature of being itself to unfold, to create, to become. And so, under this vision, every galaxy, every atom, every breath in the cosmos may be part of an unending act of inflation, the eternal flowering of reality from the false vacuum's restless heart. In that thought lies both awe and silence, a silence that stretches beyond galaxies, beyond creation, beyond comprehension. If countless universes bloom beyond our own, then the mystery of why dissolves into the vastness. What remains is not an answer, but a feeling, a quiet awareness that reality, in all its endless forms, is still expanding, and no one knows what lies beyond the edge of its unfolding light. The cosmos is vast, silent, and relentless. Its expansion unfolds not in sudden gestures, but in the imperceptible stretching of space, a motion so subtle that entire civilizations could live and die without ever noticing. And yet, hidden within that quiet drift is a force more powerful than all the stars, more pervasive than every galaxy: dark energy. To study it, humanity cannot touch it, cannot contain it, cannot see it directly. All we can do is measure its imprint, the delicate fingerprints it leaves on the universe itself. Modern astronomers hunt dark energy with tools both precise and audacious, instruments designed to trace the invisible through the visible. The Euclid telescope, launched by the European Space Agency, peers across billions of light years, mapping the large-scale structure of the cosmos. It charts the distribution of galaxies, traces the cosmic web, and seeks subtle distortions in their arrangement caused by the expansion itself. Every galaxy, every cluster becomes a tiny indicator, a point of light revealing the gravitational tug of what cannot be seen. In the deserts of Chile, the Rubin observatory trains its immense mirror skyward, capturing fleeting photons from distant stars and galaxies. Through the technique of weak gravitational lensing, the observatory measures how light bends as it passes massive structures. The bending is slight, almost imperceptible, yet it encodes information about the invisible scaffolding of dark matter and the accelerating influence of dark energy. Scientists watch the cosmos like careful cartographers, measuring the curves of light to reveal the shape of the unseen. Further back in time, the James Webb Space Telescope peers into the early universe. By observing galaxies as they existed billions of years ago, it allows astronomers to track the expansion history of space, to see how the universe's growth has changed over eons. Baryon acoustic oscillations, ripples from the primordial plasma, are measured in the distribution of galaxies, providing a standard ruler across cosmic time. Combined with cosmic shear and redshift surveys, these methods reveal a universe not only expanding, but doing so at an ever-accelerating pace. Each observation, each measurement, is an act of patience. Humanity measures shadows to know the shape of the invisible, traces distortions to map what cannot be held. In this painstaking pursuit, we confront the immensity of the unknown. Dark energy is everywhere and nowhere, a ghostly hand-stretching space, shaping the fate of all that exists. And yet, with each photon captured, each subtle bend in light quantified, we inch closer to understanding. The hunt is ongoing. Every survey, every telescope, every meticulously plotted data point is part of a grand experiment that spans the sky and stretches across time. We measure the unmeasurable, and in doing so, we glimpse the profound truth that the universe is not only alive with stars and galaxies, but also with the invisible force that drives them apart. A quiet, relentless pressure that shapes the cosmos itself. We cannot yet name it beyond the words dark energy. We cannot yet explain it, but we can trace it, follow its shadow, and marvel at a universe whose every expansion carries the echo of a force we are only beginning to understand. In the patient accumulation of data, in the bending of light and the drift of galaxies, there is a subtle poetry. The cosmos speaks in the language of motion, of acceleration, of invisible pressures, and humanity listens, measuring the unmeasurable, tracing the contours of a force older than thought, deeper than reason, and more mysterious than any star we have ever seen. Here, at the edge of knowledge, we confront the universe's secret, that its growth, its flight into the void, is governed not by the seen, but by the unseen, not by matter alone, but by the empty hand that pushes everything outward. We map it, measure it, seek it, and in doing so, we participate in a story that is still unfolding, written across billions of light years, in the bending of light, in the dance of galaxies, and in the silent, relentless expansion of space itself. For centuries, the laws of physics were taken as eternal, constants like the speed of light, the charge of the electron, the gravitational constant. They were the anchors of reality, the silent scaffolding upon which the universe built its complexity. Their values were assumed to be immutable, written into the very structure of spacetime. But as the cosmos reveals itself in ever finer detail, even these seemingly unshakable truths begin to whisper doubt. Astronomers examining the light from distant quasars have uncovered subtle anomalies, tiny shifts in the fine structure constant, a number that governs the strength of electromagnetic interactions. Across billions of years and billions of light years of distance, there are hints that it may not be fixed, that the fundamental forces may have varied, however slightly, as the universe aged. The implications are staggering. If constants drift even imperceptibly, then the rules that govern atoms, chemistry, and life itself may have danced to a different rhythm in the distant past. This possibility ripples through cosmology like a tremor. Perhaps dark energy is not constant either. Perhaps it evolves over time, a field that waxes and wanes, influencing the expansion of space in ways we do not yet comprehend. If the vacuum itself changes, then spacetime is not a passive stage, but a dynamic, living entity, responsive, unpredictable, and profoundly more mysterious than classical physics allows. Here, the tension of modern science is exposed in stark relief. Relativity presents a cosmos of smooth geometry and predictable curvature, a tapestry woven with deterministic threads. Quantum mechanics, in contrast, hums with uncertainty, a probabilistic universe where particles blink in and out of existence and fluctuations ripple across the void. Now the universe hints at another layer, a subtle instability, where the constants themselves, the anchors of physical law, may drift with the tides of cosmic time. The consequences are both philosophical and unsettling. If the numbers we hold sacred are not fixed, then the universe may be a far stranger place than even the most imaginative cosmologists have imagined. Stars, galaxies, and planets might form differently under subtle variations. Chemistry itself might change, rewriting the possibilities of life across space and time. Even the meaning of causality and prediction becomes blurred. Some theorists suggest that these shifts, if real, could be a sign of deeper forces at work, a connection between dark energy, quantum fields, and the very geometry of spacetime. Others propose that the constants are emergent, not fundamental, products of conditions set during the early universe, now slowly evolving as the cosmos expands. In either case, humanity confronts a profound lesson, that the rules we observe locally, in our Milky Way and on Earth, may not describe the universe universally. This realization is humbling. The constants that once seemed eternal may be drifting, like stars carried on unseen currents. The universe, for all its precision, harbors subtle variations that challenge our understanding. Even the laws themselves may bend and shift, revealing a cosmos that is far more fluid, far more alive than classical physics could imagine. And so, in the quiet stretching of space, in the faint pulse of light from distant galaxies, a new narrative emerges. Reality is not fixed. The constants that anchor the cosmos may sway with time, and the universe, in its vast and silent majesty, continues to expand, evolve, and confound, a living testament to the mystery at the heart of everything. Even the constants that anchor reality may drift with the tides of the cosmos, and in that subtle, imperceptible motion, we sense that the universe itself is a story still being written, not static, not final, but alive and unknowable in its full depth. The universe stretches onward, a vast, silent tide, carrying galaxies, stars, and planets upon its ceaseless current. From the cradle of the Big Bang to the present, space has been expanding, slow at first, then faster, and now it accelerates. And yet, in this expansion lies a haunting question. How does it end? What is the fate of a cosmos that is not merely large, but growing ever larger, propelled by a force we barely understand? Scientists have imagined 3 futures, each a haunting echo of the universe's relentless flight. The most familiar is the Big Freeze. In this vision, expansion continues indefinitely. Galaxies drift farther apart, their light dimming with distance, until entire clusters fade beyond the cosmic horizon. Stars burn through their fuel, one by one, leaving cold remnants in the black void. Planets grow frozen, oceans solidify, and chemical reactions cease. Entropy rises inexorably. The universe cools toward a state of near absolute zero, where motion is all but extinguished. Time itself stretches in silent, gradual decay, and all that remains is a frozen, dark expanse. A more dramatic possibility is the Big Rip. If dark energy grows stronger over time, accelerating expansion with increasing force, it could eventually overwhelm gravity, tearing galaxies apart. Star systems would unravel, planets flung into lonely trajectories, atoms themselves torn asunder. Space would stretch faster than light, and even the very fabric of matter would succumb. In the final instant, the universe would dissolve into an unrecognizable, uninhabitable void, a catastrophe written in the acceleration of expansion itself. Then there is the heat death, the ultimate equilibrium. In this scenario, the universe reaches a state of maximum entropy, where energy is evenly distributed and no gradients exist to drive change. No stars form, no planets evolve, no chemical reactions occur. The universe becomes an eternal stillness, a dark ocean of particles in uniformity, neither expanding nor contracting in any meaningful sense. Time continues, yet without change, without events, without life. Stephen Hawking reflected deeply on these fates, connecting cosmic entropy to the irreversible march of time. He pondered information loss, the question of whether the universe's history, the arrangement of particles, the dance of galaxies, the stories of stars, could survive the slow erosion of energy and structure. In every scenario, the cosmos reminds us of the scales on which it operates. Human existence, brilliant and fleeting, occupies but a heartbeat in a timeline stretching trillions of years. Every galaxy, every star we see tonight will one day vanish from view, not because it ceases to burn, but because space itself carries it beyond reach. The light we cherish, the patterns of the heavens, will be dispersed into oblivion, swept away by the inexorable expansion of the cosmos. And yet, even in this cosmic silence, there is a strange beauty. A universe that began in fire and light may end in darkness, but it carries within it the memory of every event, every fluctuation, every flicker of existence. In contemplating these endings, humanity is humbled, yet also awed. We are witnesses to the universe's story, brief travelers in a landscape beyond comprehension. The echoes of the end stretch far beyond our lifetimes, and in listening to them, we confront both the fragility and the profundity of our place within an ever-expanding cosmos. Time, space, light, all are transient, and in their inevitable fading, we glimpse the ultimate rhythm of the universe, a slow, solemn exhalation into the darkness, carrying every story, every atom, every spark of life away into infinity. The universe expands, not only in space, but in thought. Galaxies drift apart, carried by invisible hands we name dark energy, and yet their motion mirrors something deeper, the restlessness of consciousness itself, the ceaseless curiosity that drives us to look upward, to question, to measure, to wonder. Expansion is more than physics. It is a metaphor, a mirror, a silent lesson written in the movement of the cosmos. From the earliest philosophers to the modern thinkers of science, the act of observing the universe has always been an act of reflection. Einstein once noted that the most incomprehensible thing about the universe is that it is comprehensible at all. Through his equations, he glimpsed the dance of spacetime, yet recognized the limits of human understanding, the horizon where mathematics, observation, and intuition converge, and yet cannot fully capture the infinite. Carl Sagan saw the cosmos as a tapestry woven with both knowledge and humility. He reminded us that our awareness, though minute against cosmic scales, is part of the universe's story. That in observing the stars, we are also observing ourselves, the same curiosity mirrored in light years of emptiness. And Stephen Hawking, in contemplating black holes and entropy, suggested that the universe may not only evolve in time, but also encode within it the history, the memory, and perhaps the consciousness of all that it contains. Expansion, then, is not merely a measure of space or speed. It is a metaphor for creativity and awareness, for the endless unfolding of questions, for the propagation of ideas, for the emergence of life itself from the quiet void. As galaxies drift outward, so too does human thought reach into the unknown. Both are infinite in their scope, both enigmatic in their origin, and both ultimately beyond final comprehension. Perhaps in some intimate way, the universe does not expand away from us, but through us. The same force that drives galaxies apart drives awareness, drives imagination, drives the longing to understand. Space-time and consciousness may be reflections of the same principle, an infinite mirror in which every flicker of thought resonates with the unfolding of all that exists. In this vision, every star, every cosmic filament, every whisper of radiation from the dawn of time becomes a mirror of awareness, a reminder that creation, inquiry, and entropy are threads of the same vast tapestry. And as we peer into the depths of space, the stars slowly receding into the black, we are not alone. We are part of the expansion itself, observers and participants in a process that has no final edge, no ultimate answer. The universe expands, yet so does the mystery, and perhaps that is its purpose.